Much of our understanding of the modern world is built on science, and science is built on mathematics. And so this is a course about the foundations of mathematics. We want to understand what they are. We want to understand how these different mathematical ideas are really defined. And we want to really drill down to the foundations of the thing. And we want to know about the fundamental ideas of mathematics so well that we can even implement our notions in computer programs. A lot of mathematics is about communicating ideas of form, space and number from one imagination to another. And so having a sort of rigorous language that we understand right down to the foundations really improves our ability to do and communicate mathematics. We want to sort of capture the lightning of imagination in the bottle of formal mathematical systems. And as we do this, we're really going to gain a sort of fundamental understanding of what mathematics is all about to a new level of rigor. And as we do it, these ideas are going to become so much more beautiful because we're really going to understand what they are at a very kind of deep level. Okay, so we like learning, we like mathematics, but we want to put mathematics on a firm foundation so that we understand it properly, so that we can encode it in computers, so that we can really know what it is we're talking about in mathematics. That's what this course is all about. We're going to start from nothing. We're going to build up important ideas of mathematics intuitively, and then we're going to move towards how we can sort of capture those ideas in a very sort of rigorous language. And it's really a modern language, okay? So we're going to start with set theory, but we're going to look at it from a very sort of rough point of view just to introduce the important ideas. We're also going to do a similar thing with some ideas from category theory. This course is going to be self-contained, and I'm going to build up those ideas gradually, and then we're going to get to the fascinating field of type theory. Now, type theory, in a fuzzy sense, you can sort of think of it as a way to talk about set theory in a kind of computer-friendly, rigorous way. Okay, so we're going to look at type theory. We're going to see that it's actually quite easy to learn because it's really, in a sense, just a sort of reflection of certain ideas in category theory. We're going to understand how we can use type theory to really implement mathematics in computers. And then we're going to build to more sophisticated ideas, like the ideas of dependent type theory, which is the foundations of lots of fascinating modern computer languages like Idris and COQ and Lean Proof Assistant and Agda. And then we're going to go further and we're going to get to the ideas of homotopy type theory, which is a totally modern theory for which a Fields Medal was recently awarded. And what homotopy type theory allows you to do is to talk about mathematics in a very sort of rigorous and very sort of general and powerful and elegant way. And it's really, many mathematicians are sort of realizing that it's probably going to sort of become the accepted foundations of mathematics, you know, going into the future. And we really want to sort of catch up to that kind of cutting edge of mathematics and really understand as well how to do everything rigorously and how to implement things in computers. Okay, so we're going to begin very sort of humbly with some really naive ideas from set theory. Okay, and then the idea is that we're soon going to be able to start to introduce ideas from type theory and start to sort of gather up these kind of rigorous rules, which are going to be so concrete that we can literally implement everything that we're doing in computer programs and build from the ground up. So, where do we start? Let's start with the idea of a set. And for us, with our kind of intuitive viewpoint, we just think of a set as a collection of things. So here we have this set of fruits, this is a set of colours, this is a set of numbers. We want all the elements in a set to be distinct. And here's how we might express a set using the kind of traditional language of set theory. Okay, so what we're really saying here is that this set, which we're calling capital A, is the set which contains strawberry, banana and tomato. Notice we're using these curly brackets here. The set really is just a sort of unordered collection of things. So the order that we're writing these kind of elements does not really matter. So for example, we can interchange the banana and the tomato, and that is still the same set because the order doesn't matter. But we do require that these elements are distinct. So we wouldn't want to have a set that has strawberry, strawberry, banana, tomato, for example, because that would have two copies of the same element. So this is the idea of a set. And we might refer to the things in a set as the members of the set or the elements in that set. Now, I think the idea of sets is really quite fundamental. I think that it's the kind of thing that, you know, very, very young babies understand, the idea of kind of collections of things. But the other idea, which I think is also like super important for setting up the foundations of mathematics, but not anywhere near as well kind of appreciated by the general public, is the idea of a function. Okay, now a function is in a sense a kind of way that we can compare two sets. More precisely, it's a way that we can kind of associate the elements of one set with elements of the other set. More precisely, a function f from a set A to a set B is where every element in set A is sent to some element in set B. And we represent this usually when we draw these pictures, at least, by these arrows. Okay, so this function f here sends this set A to this set B. Now here B is this set of colours and A is this set of fruit. So this function f sends strawberry to red, it sends banana to yellow, and it sends tomato to red. So notice that every element in the first set is sent to some element in the second set, and it's only sent to one element. Okay, so we couldn't, for example, send strawberry to red and yellow. We can only send it to one thing. So sometimes we might call this a mapping. We might say that every element in A is mapped to some element in B. Now, this particular function has a very sort of natural interpretation because it's sending each of these fruits to the colour that it has. It's sending strawberry and tomato to red, and it's sending banana to yellow. So if you're new to the idea of functions, I strongly advise you to sit down and draw out all of the different functions from this set A to this set B. So the way that we might describe this formally, we might say that f is a function from set A to set B, but then we still need to actually describe how this function works. And so then we'd want to say how it works on the different values. So f of strawberry equals red, f of banana equals yellow, f of tomato equals red. Okay, so notice this kind of notation, because we're going to be using it a lot. The idea is that this is our function, this is our mapping from A to B, and then if we take an element of A, like the strawberry for example, and we surround it by brackets, and we put the f in front, what we're really saying is that this function f here is operating on the strawberry, and that's going to output a value in this set B, or an element of this set B, in this case red. Okay, so we say that f maps strawberry to red, f maps strawberry to red. And the way that this function works on these other values in this set A are given here. Okay, so this is really a sort of complete description of this function f. Okay, so we've got the idea of sets and we've got the idea of functions. Now, in a sort of rough sense, there's only really one other idea we need, and then we can really have at least an intuitive sort of foundation for all of mathematics. Okay, that's how powerful these ideas are. So the other idea is the idea of composition, which basically means doing one function after another one. So here we have this function f, sending these fruits to their colours. We have another function g, which sends the colour to the number of letters in that colour. So the idea is that we can compose these functions. So every function, like this one f for example, has a source set and a target set. It maps elements from the source set to the target set. Now the idea is that whenever we have functions like these, where the target set of f is the source set of g, so in other words, this function stops where this function starts, that means that we can compose those two functions. And that means there's another function that we can make by sort of gluing those two functions together. And this is really important. It's the idea really of sort of chaining together processes. And it's an important idea that we're going to sort of generalize later when we think about category theory. But for now, we're just talking about composing functions. So how do we compose these? How do we do function g after function f? Well, it's really very simple. We just start with an element of capital A, and then we go along the arrow for f, and then we go along the arrow for g, and we see where we end up. And that's what the composition g after f sends this strawberry to. Okay? So this little circle here, we can read this as saying after. And so we're making this function a new function from A to C, which we get by composing the function g after the function f. How does it work on the banana? Well, f sends the banana to yellow and g sends the to 6. So this function sends the banana to 6. How does it work on tomato? Well, tomato goes to red under f, and it goes to 3 under g. So this is the composition g after f. And if we want to give a sort of intuitive interpretation of this, we can think that it's giving the number of letters of the colour of the fruit. So this idea of function composition is really, really important, because functions, in a sense, can sort of represent aspects of things. So think about, for example, the length of a man's foot. Okay, there's a function sending every man to their foot, and there's a function sending every foot to its length, and composing those would give you the length of a man's foot. And functions are extremely important because they basically give us ways of comparing sets and ways of putting the kind of elements in sets in correspondence with one another. And this idea of composing is really, really important. So now we have all these ideas, I can explain what I think is one of the most beautiful structures in all of mathematics. And it's basically, and this is all very rough, but it's what a category theorist would call set, capital S-E-T, okay? And this is a sort of exact mathematical structure, but roughly speaking, it looks like this. We think of every single set, and we think about all the functions between the sets and all the ways that those functions can compose together. And all that information is recorded in this structure, and that's basically what this structure is. Now, this structure is, formally speaking, something called a category, and we'll get on to categories later, but I've told you the basic structure of this thing. And so what I'm really saying is that if you understand sets and you understand functions and you understand how to compose functions, you're really in a position to at least get the intuition of pretty much all of mathematics. Okay. Now, if you're new to the idea of sets and functions, then I would recommend that you do a few different exercises. Okay, so for example, write down all the different functions from a set A to a set B and think about what kind of properties they have. For example, this function here sends two elements in A to the same element in B. And there's also an element in B that has nothing sent to it. Now, as you write down all the different functions, you'll see that different functions have different kinds of properties. And so it's a really good idea to get used to those. But anyway, we have this idea of composition, but let's make sure that we understand what it means. Let's formalize this idea. Okay, so since this idea of function composition is really important for us, let's write down, at least sort of semi-formally, what this means. Okay, so the composition of this function f, which is a function from set A to set B, and this function g, which is a function from set B to set C, is this function here that we call g after f. And this is a function from set A to set C. But how is this function defined? Well, this says how it's defined. Okay, so it's defined so that for any element x in A, so in this scenario, for example, x might be strawberry, but x could really be any element at all of this set A. Well, for any element x in A, we're going to have that doing g after f on x is defined to be what we get if we do f on x and then we do g on that. If you're new to these ideas, I really strongly recommend that you sit down and do lots of examples, thinking about how you can compose functions. You can think about functions which go from a set to itself and think about how they kind of give you an idea of dynamics in some sense. So this is a very interesting idea. Let's say we have a function like this that sends 1 to 2 and it sends 2 to 1 and it sends 3 to 2. Let's call this function h from this set D to this set D. So this is a function from a set to itself. And we have an interesting way of visualizing this kind of thing. We can just draw one copy of this set D and think about how this sort of function sends elements around kind of internally. So we can just draw the picture internally. So 1 is sent to 2. And 2 is sent to 1. And 3 is sent to 2. So we could draw it like that. And in a sense, this gives us a sort of elementary way to think about what are called dynamical systems, okay, which are basically systems that change over time that we want to model mathematically. So we could think that this function h here is sort of telling us how over time. So we have this system with states 1, 2 and 3, and if the system's in a particular state, let's say 3 here, then at the next time step it's going to be in the state h of 3, which is 2. Okay, so this is telling us how the system changes state over time. And so if we think about composing this function h with itself, that would be telling us how this system sort of evolves over many time steps. So for example, doing h after h is like walking along 2 of these arrows, and such a process would be like how this dynamical system changes over 2 time steps. And that would send 3 to 2 to 1. Okay, so under 2 steps of updating this system, if it was in state 3, then it would be in state 1 afterwards. And so you can think about the kind of dynamics that you get when you sort of repeatedly apply a function from a set to itself. And again, if you haven't thought about that kind of thing before, I really strongly urge you to think about it, because these are really the kind of things which you can think about, you know, forever, because these are really the kind of things that you can get very deeply into. They're very easy to think about, they're very fundamental, and it's a kind of thing that you can sit down with a pen and paper and draw out lots of examples and, you know, for yourself try and build up the theory. I mean, it's great to try and learn from courses and things, but it's in a sense much better if you can sort of sit down and try and discover the theory for yourself and express it in your own language. Okay, so I'd just like to also speak briefly about what to expect coming up in this course, okay? Because basically the route that we're going to take is we're going to start with intuitive ideas of set theory, and we're going to be working towards category theory. And a way that you can think about this course is that we're sort of going to category theory, taking these amazingly powerful ideas and then using them to shine light on all sorts of other things, like ideas about logic and set theory and the foundations of mathematics. And everything can become so clear if we use these ideas of category theory. And so this course is self-contained, but the kind of difficulty level is a bit strange, because we start off really quite simple, I think, with ideas of set theory, but then we go to category theory and we're going to look at these sorts of universal constructions, which some people would say kind of lie behind all different forms of thought. And these are a little bit abstract, but they are extremely profound. And so as we focus on those, there might be a bit of a spike in difficulty, and it won't last long. It only takes an hour or so to introduce these different notions. And I just wanted to prepare you for this, because if you're following these videos, if it gets to this point, you know, 2 or 3 videos in, when everything starts to become rather abstract, don't worry, because the thing is that all we're really doing is introducing these very, very general kind of constructions in category theory. And then afterwards, we're going to be applying special cases of those constructions. And so, in a sense, you don't even really have to understand these kind of universal constructions of products and exponential objects and things like that. Because as we continue, we're going to be applying those notions. And as we do that, you don't really need to understand the general rules. You can just look at these specific examples, which are well defined in their own sense, okay? So it's a little bit like, for example, I'm sure there are some very fine astronomers who don't have a very good understanding of general relativity. It's probably useful to know about general relativity to understand the kind of background notions, but it's not really necessary. And in a similar way, some of the category theory we're going to cover at the beginning sheds a lot of light on what we're doing, but you don't need to worry about understanding it all straight away. On the other hand, we are going to see that these ideas from category theory shed so much light on all these different ideas in logic and set theory and all sorts of things to do with thinking and the foundations of mathematics. So if you do sort of find the coverage of these ideas too brief and you really want to roll up your sleeves and understand these notions more thoroughly, I do have this series, Category Theory for Beginners, where I talk about all of these different ideas much more kind of methodically with lots of examples and so on. Anyway, the point is that if you can sort of ride through this initial kind of introduction of this rather abstract material, and, you know, maybe just like put your YouTube speed on double or something if things start to get too abstract, it's really worth riding it out, because Number one, we're going to see lots of applications and examples of the ideas here. So what follows is very useful for understanding these abstractions. But more than that, there's really quite a magical point in this course, in my opinion, because we start by introducing, we talk about set theory and then category theory, then we go to logic and we go to type theory, and somewhere around this kind of transition point, we start to see that everything is all the same in some sense, that the structure of set theory and the structure of logic and the structure of lots of type theories are, there's so much similarity between them. And we can see all this, using our category theory, and it's really a very, very interesting kind of thing to understand. So that's the basic kind of structure of the course, and I hope you enjoy it.